Hi, Chem 181. There were some issues with the video file last week, so I'm going to do material both from last week and from this week. For part 1, we can go over empirical and molecular formulas, and part 2, we can do the balancing equations and limiting reactants. So to get started, if I had a formula for hydrogen peroxide, there are three different methods I can use to represent it. The empirical formula is going to be our simplest notation. It is going to have the smallest whole number ratio between the elements in your compound. So for this, I can reduce and represent it that way. In molecular formula, you show the actual number of atoms involved. So here, you do not reduce your subscripts. And the third way is a structural formula, and that shows, instead of subscripts, how the atoms specifically join together. And that will come up later in the semester, I believe in chapter 7. But if I asked you to find me an empirical formula, there are 3 steps you can take. First, you convert to moles of each element. Second, you are going to divide your values by the smallest number of moles, and so that smallest number that you're going to calculate in a few minutes, that's going to go on the bottom. And you divide those numbers to find your subscripts. So let's say in a more general example, I asked you to find the empirical formula of C2H4N2. So using our whole number ratios that we can reduce by, and then for the second example, notice here, this is a 1. Ignore it for now. Go ahead and reduce everything else. So everything else here, we can again use 2. Technically, you are dividing by 2 here, but since you don't have half of an element, you round up. So this just stays the way it is. And let's see here. You can also use percent composition to find empirical formulas. And those rules I had set up front, they're going to be very similar to percents. First, you are going to convert, and if something is, say, 11.19%, that is going to be, let's say, like hydrogen. That means it's going to be 11 grams of hydrogen. And then from there, you convert to moles. So if I asked you to find the empirical formula of a compound that is 30.4% nitrogen and 69.6% oxygen, follow your conversion rules. So first, take care of nitrogen. I have 30.4 grams of nitrogen, and I know that 14.01 grams are in 1 mole of nitrogen. And once I convert that over, this will give you 2.17 moles of nitrogen. And we're going to do the same thing with oxygen. So I know that I have 69.6 grams of oxygen. And I also know that for 16 grams of oxygen, I am able to get 1 mole of oxygen. When I convert that over, I'm going to get 4.35 moles of oxygen. Now, our second step was to divide. So between the 2 of these, it would be the nitrogen. So you're going to stick that on the bottom, and just remember to keep track of where you put things, for that way you won't get mixed up when you do your subscripts. So we're going to divide those two, and that's going to give you about 2. And remember that this is a ratio, so it's actually 2/1, if that'll help you. So now you apply your subscripts. And that's your empirical formula for your compound. What if I asked you for the molecular formula? I will go up, and for the molecular formula, there are 2 steps. One is just the big one. So step 1 of the molecular formula is to find the empirical. And once you do that, step 2, you're going to multiply your empirical by what we call the N factor. And the N factor is going to be the molar mass of your compound divided by the molar mass of your empirical formula. Okay, so let's do an example. This is from your book. And for those of you that don't have it, go ahead and write down what you think is important. Go ahead, pause, and then keep going. So if I asked you for the molecular formula of dimethylhydrazine, which you are told is made up of carbon, hydrogen, and nitrogen. And using, you can fit these into these steps and solve. So you are told in the problem that your compound has a molar mass of 60.10 grams per mole. You also know that 2.89 grams of this compound combined with an excess of oxygen and that gave you carbon dioxide and water. So here, you were given the products. You need to find the reactants. So you need to know what goes right here. And so you don't panic. You don't need to know dimethylhydrazine off the top of your head. That's not what's expected. Instead, you're supposed to use the rules of molecular formula, which is to find the empirical formula. So first, we are going to convert everything that we were given to moles. So first, let's start off with our carbon dioxide. We have 4.190 grams of CO2. And by calculating the molar mass, you find that there are 44 grams of CO2 in 1 mole of CO2. And you also know that for every 1 mole of carbon, there is 1 mole of carbon somewhere in your product. And converted, you will have 0.05. Those are your moles of carbon. Next, you are going to find your moles of hydrogen. So we will first do our water. So we know that we have 3.428 grams of water. And we also know that there are 18 grams of water in 1 mole. And in 1 mole of H2O, we know there are going to be 2 H's somewhere in our product, in our reactant. Converted, that is going to give you 0.380 moles of hydrogen. Now, we know that there are 3 components to this reactant that we're trying to make. There's carbon, hydrogen, and nitrogen. We know that the total of those are going to make your reactant. Therefore, to find nitrogen, take what you know. We know that if we this minus the mass of this, we can find nitrogen. What you're going to do here is you're going to sort of work backwards. You simply can't add the carbons and hydrogens that you have together as you have them. So instead, you're going to convert to grams, but use this molar value, these molar values that you just found, and that's how you'll find your most precise amount in grams. So I know that I have 0.09523. And I know that in 1 mole of carbon, I have 12 grams of carbon. And multiplying that across, that is going to give me 0.43 grams of carbon. And we're going to do the same thing for hydrogen. So I know I have moles of hydrogen. And I know that in 1 mole of hydrogen, there are 1.008 grams of hydrogen. And with that conversion, I get 0.385 grams of hydrogen. Now, finally, you can add these 2 together. And so that's over here. And remember, you were told this in the very beginning, way up here. Okay, so just plug those in and do your subtraction. And you find that you have that in this, you're going to have 0.0915, which is going to round up to 0.152. Moles of nitrogen. So, step 2 is where we're going to divide. And remember, you have to pick out the smallest number and divide all the values by that number. Luckily for us, let's see here, compare this number, and this number, and this number. So carbon and nitrogen are pretty much the same. They're just different by that 1. So that'll make it a little bit easier for us. We're going to divide each of these. And this is going to give you 4, it's going to give you 1. And apply your step 3 of this is going to be apply your integer subscripts. So C1, H4, N. Now remember, we want the molecular formula. This is the empirical formula. The empirical formula is just the simplest formula. We want to know what integral of this was used in this specific experiment. So we have to multiply, we have to find and multiply by our n factor. And our n factor is, again, our molecular weight divided by our empirical. Weight. And remember, we were told in the very beginning that our compound has a molecular weight of 60.10 grams per mole. So that's the molar mass. Now we find our empirical weight by applying our empirical formula. So here, and you add all of that up together, and that'll give you about 30. We plug that in to divide, and we're going to get a value of 2. So that is our n factor, and that is what we're going to multiply to our subscripts to obtain our molecular formula. So that gives us okay. Now, you can also use chemical formulas to find the percent composition. So let's say we go over here. Okay, let's say I asked you for the mass percents making up iron 3 oxide. So using the cross method, I know that this went here, this over here, so that became this. What I want to know is what percent mass does the iron take up in the compound, and what percent of this compound does the oxygen take up, because unfortunately it's not as easy as just 50-50. So what we're going to do first is, again, we are going to go from moles to grams. I know that I have 1 mole of this compound, and in 1 mole of this compound, I have 2 moles of iron. And I know that in 1 mole of iron, looking at our periodic table, I have 55.85 grams of iron. Calculating that across, I have 111.7 grams of iron. Now, if this were required, or if this is a bigger compound, I would do the same thing for oxygen. But since there are only 2 components in this compound, we can actually skip it. Instead, what we're going to do is find our mass percent of iron first. So we take the total mass of our iron that we obtained, and then we take the total mass of our compound. And when you add all that up together, that is going to give you Using the molar values, 159.7 grams. And dividing that and multiplying by 100 to convert to a percent, that is going to give you 69.94 percent. So 69.94% of iron 3 oxide is going to be iron. To find oxygen, this is a little bit easier. I just take 100 and I subtract iron's portion. 0.06, and I know that 30.06 of our compound is oxygen. Okay, next we'll go to part 2, which is going to be balancing equations. Go here. Okay, so balancing chemical formulas. Okay, so first we have to take note, you have to take note of what you have to identify what you need. A general rule is to just list out all the elements on each side of the equation and then just count how many there are so you can compare and see what it is that you need to get to. You can pause the video to try it and then come back. I'll just go ahead and go through these. So I know that so far we are okay with our hydrogens. It is our sulfur and our oxygen that are causing the issue. So first things first, I will look at Okay, so looking at this, again, if you're wondering where I got some of these numbers here, just remember to, again, look at every part that has its subscripts. Don't forget those. Now, this next one is a little bit tricky, and sometimes you have to just play around. This one I had to for a little bit. If you only have one left, if everything else is even, don't be afraid to play around with the others and screw them up. You can always balance it out again later. So, Hold on. I'm sorry. The back of the book is wrong with this one. Hold on. This isn't working. It says 4, 9, 4, 10H2O, 2N2. Hold on, your oxygens aren't working. There's too many. Oh wait, no, 18, duh, wow. Okay, there we go. Sorry about that, okay. Okay, so balancing equations, moving on. We use balancing equations for the next part, which is with limiting reactants. And a limiting reactant is the minimum of your most important substance that is going to allow you to make the product that you want. So let's say I had like 4 hamburger patties and 5 buns. Because this is going to be our limiting reactant. No, sorry. This is going to be our limiting reactant. We can only make a maximum of 4 burgers. So it's the piece of your equation on your, your reactant side over here that's going to establish how much you can get away with to make your product. It is not always going to be the smallest number up front. What happens is it depends on what happens during the conversions and the ratio to the product. So there are just a couple of basic steps. Step 1 is that you always start with your balanced equation, or you do not have the right ratios and everything will be off. Second, you are going to calculate each reactant for the moles of product that it can make. And step 3, you're going to compare the values. And the smallest that you find with these, that is your hamburger patty or your limiting reactant. So if I asked you to find the limiting reactant between antimony and iodide when you have 1.2 moles of antimony and 2.4 moles of iodide. So first, this is not balanced, so we have to take care of it. And next, we have to calculate for the limiting reactant. So I was told that I have 1.2 moles of antimony. And by this ratio, I know that for every 2 moles of antimony, I have 2 moles of my product. Based on this, I can calculate, and the most that antimony can contribute and the most product I can make with this amount of antimony is 1.2 moles of product. And this is a 1-to-1 ratio right here. So that makes sense. Next, you do the other one. So I am told, I know that I have 2.4 moles of iodide. And from this equation up here, I know that for every 3 moles of iodide, I can make 2 moles of my product. So go down here, come on. And calculating that across, and the most iodide can make in this scenario is 1.6 moles of product. And step 3, we compare the two, and this one is smaller. So that means that clearly antimony is your limiting reagent. And from here, you would calculate this into moles of moles to grams for your theoretical yield. So we go over here. I have 1.28 moles of antimony, and I have every 2 moles. I get 2 moles of antimony triiodide, and I know that in 1 mole of this, I take the molar mass to convert it to grams. So I know that in 1 mole of antimony triiodide, calculating out, I have 502.47 grams. And calculating that out, that gives me 503.67 grams of antimony triiodide. Okay, next thing this leads into is theoretical yield. Usually right after you have your theoretical yield, you're going to be asked to find your percent yield. And this is a little different from percent composition that we did earlier, because before it was about determining what percentage of formulas components are. Percent yield is how much product you did obtain in the lab. So to find percent yield, you must first, 1, find the limiting reactant, then 2, convert it to a percent. And what you do is you're going to take your theoretical, so like over here, and you're going to divide your actual that you get in lab by your theoretical, and you multiply that by 100 to get your percent yield. Now, typically, you're not going to get 100% yield in lab because while matter is not created or destroyed, some is converted to phases that you can contain, like gases. Also know that in some special cases, you actually can get over 100% yield if your product did something like solidify when it was supposed to be all liquid, or if you were supposed to take a solid and it was wet because water got trapped in it. Those impurities will increase your mass, and the greater the mass, the greater the yield, and that increases your percent. So if I asked you for the theoretical yields of phosphorus, let's see here, phosphorus triiodide, and it was mixed with water, you would get phosphorus acid and hydroiodic acid. If I used 25 grams of each mixed together, how many grams of phosphorus acid could I form? So we're focusing on this one. So by asking for theoretical yield, I am asking for 3 things. I am asking for a balanced chemical equation to identify the limiting reactant, and then find your theoretical to calculate. And this one actually I had balanced already for you, so we are good. So next we convert everything from grams to moles to figure out which one is going to be our limiting reactant. So we know that there are 25 grams of phosphorus triiodide, and I also know, let me look here, that there are 111.68 grams phosphorus triiodide in 1 mole. And for every 1 mole of phosphorus triiodide, I have 1 mole of my product. So I go ahead, put that in, and my conversion factor, everything is good. So I multiply all that across, and I am going to get 0.0607 moles of product when in an experiment with 25 grams of phosphorus triiodide. Now, I do the same thing with water. I have 25 grams of water. I know that there are 18 grams in 1 mole of water, and this equation up here for every 3 moles of water, I get 1 mole of product. So, and I know that, let's see here, so 3 moles, 1 mole, and multiplying that across, that will give us 0.46 moles. So, looking at this is a small number. Therefore, phosphorus triiodide is our limiting reagent. So this is what we convert back to grams of product to get our theoretical yield. So and there are calculating for the molar mass, I get 81.99 grams, and calculating across, that is going to give me 4.979 grams of phosphorus acid. And let's see here. So I want this to be 2 sig figs, so 5.0 phosphorus acid. That are how many grams of phosphorus acid, a phosphorus acid that should form. Now, if I told you that in lab, what you actually made was 3.5 grams. From this, calculate the percent yield. So again, what you're going to do is actual from lab over your theoretical, which is 5. Divide these two, multiply by 100, and you get a 70% yield. Okay, I know that was a lot. If you have questions, please feel free to email and I can cover it in the next section.